Welcome to this presentation on feedback control systems. I am Rajanikant A. Metri from the Department of Electrical Engineering at Rajarampu Institute of Technology. This institute is an empowered autonomous body approved by AICD and affiliated with Shivaji University Kolhapur. If you need to reach me during or after this presentation, my email and mobile number are provided here. Let's dive into the topic and explore the fundamentals and applications of feedback control systems. Now, let's dive into control system engineering. This field focuses on designing and managing systems that regulate the behavior of other devices or systems. Essentially, control systems help maintain desired outputs despite changes in internal or external conditions. Whether it's an automatic thermostat keeping your home at the perfect temperature or complex industrial machines operating with precision, control system engineering is at the core. Throughout this presentation, we'll explore the fundamental principles, types of control systems, and practical applications that demonstrate how these engineered controls shape the technology around us. After completing this session, students will be able to represent physical systems through mathematical models, which is fundamental to understanding system behavior. They will also learn how to calculate time domain specifications for second-order systems, enabling them to evaluate system performance accurately. Additionally, students will analyze various systems using both time domain and frequency domain tools, gaining a comprehensive understanding of system dynamics. We will also compare different controllers and compensators, which are essential for designing effective control systems. Finally, students will apply state space techniques to analyze and interpret multiple input, multiple output, or MIMO systems, broadening their capability to handle complex control scenarios. This course, E313, titled Feedback Control System, provides a solid foundation in these critical control engineering concepts. On this slide, we see the mapping of course outcomes to program outcomes and the relevant weeks of the course. The first outcome focuses on representing a physical system as a mathematical model. This links to program outcomes 1 and 5 and is covered primarily during weeks 2, 3, and 6. Next, calculating time domain specifications for a second-order system helps students understand system behavior over time. This connects to program outcomes 1, 2, and 5 and is also covered in weeks 2, 3, and 6. The third outcome involves analyzing systems using both time domain and frequency domain methods, deepening analytical skills, and aligning with the same program outcomes and weeks as before. Comparing different controllers and compensators is a fourth outcome, relating to program outcomes 1, 3, and 5, and is addressed mainly in weeks 3, 4, and 6. Finally, the fifth outcome emphasizes the application of state space techniques to analyze multi-input and multi-output systems, engaging a broader set of program outcomes, 1, 2, 4, and 5, and spanning weeks 2, 3, 4, 6, and 8. This comprehensive mapping ensures that each course outcome is clearly tied to the program goals and the instructional timeline. After completing this topic, you will have a solid understanding of time domain analysis for control systems. We'll start by exploring the time response characteristics of first-order and second-order systems, which are fundamental to predicting how systems behave over time. Then, you'll learn how to determine steady-state error for different types of systems, helping you assess their accuracy and performance. We'll also cover key time domain specifications like rise time, settling time, peak time, and overshoot, so you can quantify the dynamic response of second-order systems. Additionally, we'll examine how variations in system parameters affect both open-loop and closed-loop responses, giving you insight into system sensitivity and robustness. Finally, we'll analyze the critical role of feedback in improving system stability, enhancing response, and rejecting disturbances, which are essential concepts for effective control system design. Here, we're focusing on the concept of impulse response. Essentially, impulse response describes how a system reacts to a brief input signal, called an impulse. This response reveals important characteristics about the system's behavior over time. By analyzing the impulse response, we can understand how the system processes or filters signals, which is crucial in fields like signal processing, communications, and control systems. It's a foundational tool for predicting system performance and designing efficient algorithms. Impulse response is a fundamental concept in signal processing and system analysis. It describes how a system reacts over time to a brief input signal, often called an impulse. By studying the impulse response, we can understand behavior and characteristics of the system, such as how it filters or modifies signals. It essentially tells us everything about how the system processes any input, making a powerful tool for analyzing and designing systems in fields like audio engineering, telecommunications, and control systems. Understanding the impulse response allows us to predict the output for any given input by using techniques like convolution. This makes it essential for both theoretical analysis and practical applications. Let's take a closer look at the impulse response of a first-order system. One key thing to understand is that the initial slope of the response is inversely proportional to the time constant. This means that if the time constant is smaller, the initial rate of change is steeper. After one time constant has passed, the system's response completes about 63% of its total transition. This is a critical point to remember when analyzing system speed. Also, the response decays back to zero as long as the system's pole, denoted by sigma, is negative, which ensures stability. Now, when we increase sigma, the pole moves further into the left half of the complex plane, which results in a smaller time constant and a faster system response. So, the bigger the sigma, the quicker the system reacts and settles. This relationship between the pole's position, the time constant, and the response speed is fundamental in understanding first-order system dynamics. Now, let's take a closer look at step response. This concept is fundamental when analyzing how a system reacts to sudden changes or inputs, specifically a step input. Understanding the step response helps us predict system behavior, such as stability and speed of reaction. Key aspects to focus on include the rise time, overshoot, settling time, and steady state value. Each of these parameters provides insight into how quickly and accurately the system reaches its desired output after a step change. By examining these characteristics, we can evaluate performance and make necessary adjustments to improve system response. Here, we're looking at a first-order system without zeros, which is characterized by the transfer function shown. When the input to the system is a unit step, represented as Rs equals 1 over S in the Laplace domain, the resulting output Cs can be found by multiplying the transfer function by this input. By taking the inverse Laplace transform, we obtain the time domain step response of the system. A key aspect to focus on is a parameter in this response. This single parameter completely defines the transient behavior of the system. One important point is when time t equals a reciprocal of, that is, t equals 1 over at this moment. The response has a notable characteristic, which helps us understand how quickly the system reaches steady state after the step input. Essentially, it governs the speed of the system's response. Higher values of a lead to faster settling times, while smaller values indicate slower responses. This makes a crucial for designing and analyzing first-order systems. Here, we define the time constant, which is a reciprocal of the parameter. The time constant essentially measures how quickly the system responds. Specifically, it represents the time it takes for the exponential term, e to the power of negative at, to decrease to about 37% of its starting value. Another way to look at it is through the step response. The time constant is the time required for the output to reach 63% of its final steady state value. Since the reciprocal of the time constant has units of 1 over seconds, which corresponds to frequency, we often refer to as the exponential frequency. Understanding the time constant is critical because it characterizes the speed of response for a first-order linear time invariant system, making it a fundamental parameter in analyzing system dynamics. Let's talk about two important transit response specifications, rise time and settling time. Rise time is the duration it takes for the response to go from 10% to 90% of its final value. We determine this by calculating the difference in time when the output reaches 0.1 and 0.9 times its steady state value. Settling time, on the other hand, is the time it takes for the response to enter and remain within 2% of the final value. This means the system's output has effectively stabilized within a small margin around the steady state. By setting the output to 0.98 or 98% of the final value and solving for time, we find the settling time. Both these specifications give us valuable insight into how quickly and accurately a system responds to changes. Now, let's focus on steady state response specifications. These are important criteria that help us understand how a system behaves once it is settled and is no longer changing over time. Key specifications typically include parameters like steady state error, which tells us how close the output is to the desired input, and settling time, which indicates how quickly the system reaches a steady state. Understanding these specifications allows us to design and tune control systems for optimal performance, ensuring accuracy and stability in the long run. Let's look at the step response of a first-order system. One key point to understand is that the initial slope of the response is inversely proportional to the time constant, meaning that a smaller time constant results in a steeper initial slope. After one time constant, the system completes about 63% of its total transition, which is a useful benchmark for evaluating response speed. The system is considered almost fully settled after about 7 time constants. Additionally, when the parameter sigma, which corresponds to the pole of the system, increases, the time constant decreases, leading to a faster response overall. This relationship highlights how tuning the pole location can directly impact how quickly the system responds to changes. Let's take a closer look at an example of a first-order system. First-order systems are characterized by having a single energy storage element, such as a capacitor or an inductor, which leads to a specific type of response behavior. Typically, the system's output changes exponentially in response to an input, either rising or falling toward a steady state. Understanding how these systems behave is crucial because they form a foundation for analyzing more complex control systems. In this example, we'll explore how the system responds over time, highlighting key parameters like the time constant, which defines the speed of the system's response. This helps us predict and design systems that behave in a reliable and controlled manner. Here we have an example of a first-order system. A first-order system is characterized by a differential equation that has a single energy storage element, which leads to a response that can be described by a simple exponential function. These systems typically exhibit behavior where the output gradually changes over time and approaches a steady state without oscillating. In this example, we'll see how the system responds to an input and how the time constant determines the speed of the response. Understanding this example helps us grasp the fundamental dynamics of many real-world systems, such as RC circuits, thermal processes, and more. On this slide, we'll focus on pole location and stability, which are crucial for ensuring the safety and reliability of our infrastructure. Properly positioning poles helps us maintain structural integrity while accommodating environmental factors like soil conditions and terrain. Stability is essential to prevent poles from leaning or falling, especially during adverse weather. By carefully selecting pole sites and considering factors such as soil strength and load requirements, we enhance the overall durability and safety of the installation. Understanding these concepts helps us design and implement more resilient support systems. Now, let's dive into second-order systems. These systems are a bit more complex than first-order ones because their behavior is governed by a second-degree differential equation. This means the system's response depends not just on the current input, but also on its past states and how fast those states are changing. Understanding second-order systems is crucial because many real-world systems, like mechanical vibrations or electrical circuits, fall into this category. We'll explore their characteristics, such as their natural frequency, damping ratio, and how these factors influence the system's response. This will give us a clearer picture of how to analyze and predict the behavior of more complex dynamic systems. Now, let's dive into second-order systems. These systems are fundamental in understanding more complex behaviors in engineering and control theory. Unlike first-order systems, second-order systems have two energy storage elements, which means their responses can be more dynamic and varied. You'll often see characteristics like oscillations, overshoot, and damping, which we analyze to design stable and efficient systems. Grasping these concepts is crucial because they apply to everything from mechanical vibrations to electrical circuits and beyond. As we move forward, we'll explore how these systems respond to inputs and how we can control their behavior effectively. Now, let's dive into second-order systems. These systems are characterized by differential equations where the highest derivative is of the second order. Unlike first-order systems, second-order systems can exhibit a richer variety of dynamic behaviors, such as oscillations and overshooting. Understanding these systems is crucial because they model many real-world processes, from mechanical vibrations to electrical circuits. We'll explore their properties, response types, and how parameters like damping and natural frequency influence their behavior. This knowledge will help us predict and control system performance more effectively. Let's dive into second-order systems. These systems are characterized by differential equations where the highest derivative is of second order. Unlike first-order systems, second-order systems can exhibit more complex behaviors such as oscillations, overshoot, and damping effects. Understanding these dynamics is crucial because they appear frequently in engineering applications, such as mechanical vibrations, electrical circuits, and control systems. By studying the response of these systems, we can predict how they will behave under different inputs, which helps in designing stable and efficient systems. Now, let's dive into second-order systems. These systems are characterized by differential equations where the highest derivative is of the second order. What makes them particularly interesting is their dynamic behavior, which includes oscillations and complex responses that you don't see in first-order systems. Understanding second-order systems is crucial because they model many real-world processes, from mechanical vibrations to electrical circuits. Throughout this section, we'll explore their natural frequency, damping ratio, and how these parameters influence the overall system response. This will give us a solid foundation for analyzing and designing more complex systems effectively. Now, let's dive into second-order systems and their responses. These systems are a bit more complex than first-order ones because they incorporate elements that cause oscillations, like springs or inductors. Understanding their behavior is crucial since many real-world systems, from mechanical to electrical, are second-order. We'll explore how these systems respond to different inputs, focusing on characteristics such as damping, natural frequency, and how these affect the overall system performance. This foundation will help us analyze and design systems that behave predictably and efficiently. Now, let's talk about second-order systems, which are fundamental in understanding many dynamic behaviors. First, we have the natural frequency, denoted as omega n. This is essentially the frequency at which the system oscillates when there is no damping at all. Imagine a series RLC circuit where the resistance is shorted out. The frequency at which it naturally oscillates is its natural frequency. Next, we have the damping ratio, represented by the Greek letter zeta. This ratio is important because it relates the rate at which the oscillations decrease over time to the natural frequency. It tells us how quickly the system's oscillations die out. What's interesting is that this ratio stays the same no matter how you look at the timescale of the response, making it a very useful parameter for analyzing the system's behavior. Both of these concepts are tied together in the general second-order transfer function, which mathematically describes how the output of the system responds to an input, considering both the natural frequency and the damping ratio. Understanding these parameters helps us predict and control system responses effectively. On this slide, we're focusing on second-order systems, which are really important in understanding how many physical and engineering systems behave. The key concept here is the second-order response and how it varies as a function of the damping ratio. The damping ratio essentially tells us how oscillations in a system decay after a disturbance. When the damping ratio is low, the system tends to oscillate more before settling, while a higher damping ratio means the system quickly stabilizes without much overshoot. This relationship is crucial because it helps us predict system behaviors like vibrations, stability, and how quickly a system returns to equilibrium. Understanding these responses allows engineers to design systems that behave in desired ways, whether it's minimizing vibrations in a mechanical structure or controlling the response of electrical circuits. Let's dive into second-order systems and their responses. These systems are characterized by differential equations of the second order and exhibit more complex behavior compared to first-order systems. What makes them particularly interesting are the different types of responses they can have, such as overdamped, underdamped, and critically damped. Each response type describes how the system reacts over time to changes, like sudden inputs or disturbances. Understanding these responses is crucial because they help us predict performance and stability of many engineering and control systems, from mechanical vibrations to electrical circuits. We'll explore these concepts in detail to see how the damping ratio and natural frequency affect the system's behavior. Now, let's look at the step response of an underdamped second-order system. In such systems, the response to a step input doesn't just smoothly rise to the final value. Instead, it oscillates around that value before eventually settling. This behavior occurs because the system has complex conjugate poles with negative real parts, which means it experiences both oscillation and damping. Understanding this response is crucial because it tells us how the system behaves in the presence of sudden changes, which is common in many practical control systems. The key takeaway is that an underdamped system reacts dynamically with overshoot and oscillations before stabilizing. Recognizing and analyzing this helps us design systems with the desired performance characteristics. Let's take a closer look at the specifications of underdamped second-order systems. These systems are characterized by oscillatory responses that gradually settle over time. Key performance metrics include the percent overshoot, which tells us how much the system surpasses its target value before settling. Another important measure is the settling time, which defines how long it takes the system to stabilize within a certain error band around the final value. We also consider the damping ratio, which influences the nature of the oscillations, and the natural frequency, which determines how quickly the system oscillates. Understanding these specifications helps us design and analyze systems to meet desired performance criteria efficiently. Here, we're focusing on two key parameters in underdamped second-order systems: the damp frequency, omega d, and the exponential damping frequency, sigma d. The damp frequency, omega d, represents the frequency of oscillation that occurs when the system is underdamped, and it's derived from the imaginary part of the system's pole. On the other hand, sigma d corresponds to the magnitude of the real part of the pole and describes the rate at which these oscillations decay over time. Understanding these frequencies is crucial because they tell us how quickly the oscillations will diminish and how fast the system oscillates before settling down. This insight helps in designing systems that respond efficiently while avoiding excessive oscillations. Let's take a closer look at the specifications for underdamped second-order systems, focusing on the criteria for a plus or minus 1% settling time. This means we're interested in how long it takes for the system's response to settle within 1% of its final value after a disturbance or input change. Settling time is a key performance metric because it tells us how quickly the system stabilizes without excessive oscillation or delay. Understanding these specifications helps us design systems that balance responsiveness with stability, ensuring that the system behaves predictably and efficiently in real-world applications. Here, we have an example problem where we are given a transfer function, and our task is to find three key specifications: the peak time, the settling time, and the peak overshoot. These parameters are crucial for understanding the dynamic responsive system. The peak time, represented as Tp, is the time it takes for the system response to reach its first maximum peak. In this case, it is 0.475 seconds. The peak overshoot, shown as a percentage, indicates how much the response exceeds a final steady-state value during the transient phase. Here, it is 2.838%, which tells us the system slightly overshoots before settling. Lastly, the settling time, denoted as Ts, is the time required for the system to remain within a certain percentage band around the final value, which is 0.533 seconds for this example. Understanding these specifications helps in designing and tuning control systems to achieve desired performance and stability. Now, let's take a closer look at the specifications of underdamped second-order systems by examining their step responses. When analyzing these systems, we focus on how the poles move in the complex plane and how this movement influences the response. There are three main cases to consider. First, when the poles move while maintaining a constant real part. Second, when the poles move with a constant imaginary part. And third, when the poles move with a constant damping ratio. Each of these scenarios affect parameters like oscillation frequency, damping, and settling time differently, which in turn changes the shape of the step response. Understanding these variations helps us design and predict system behavior more effectively. Now, let's take a closer look at examples of underdamped second-order systems and their key specifications. Understanding these examples will help us see how the theoretical concepts apply to real-world scenarios. We'll focus on characteristics like overshoot, settling time, and damping ratio, which are crucial for predicting system behavior. This will give us a clear picture of how these systems respond over time and how we can control or utilize that response effectively. Now, let's look at some examples of underdamped second-order systems. We'll focus on the key specifications that define their behavior. These specifications help us understand how the system responds over time, including characteristics like overshoot, settling time, and oscillations. By examining these examples, we can see how different parameters affect the system's performance and how to design for desired outcomes in real-world applications. When dealing with systems that have more than two poles or include zeros, the formulas we derive for performance specifications like percent overshoot, settling time, and peak time don't directly apply. However, there's a useful workaround. Under certain conditions, these higher order systems can be approximated as a second order system by focusing on just two complex dominant poles. This means that even for more complex systems, we can analyze their behavior by identifying the dominant poles and applying the second order system formulas to get a good estimate of their response. This approach simplifies the analysis and helps us understand the system's performance without needing to dive into more complicated calculations for every pole or zero present. Here, we're focusing on how the system responds when additional poles are introduced. Adding poles to a system generally impacts its stability and dynamic behavior. Each pole corresponds to a natural frequency of the system, and additional poles can slow down the response, potentially causing more oscillations or even instability if not properly managed. It's important to analyze how these extra poles affect the overall system performance to ensure it meets design specifications. Understanding this helps us anticipate changes in speed, damping, and stability, which are critical for designing effective control systems. Here, we're looking at how the placement of additional poles affects the system response. In the second case, T2, the third pole is located at -10, which is farther away from the dominant poles. This placement provides a better approximation of the original system, T1, because the dominant poles primarily govern the system's behavior. In contrast, for T3, the third pole is much closer to the dominant poles. This proximity actually introduces more error into the system's response, making it less accurate compared to T1. So, the key takeaway is that having additional poles farther from the dominant poles tends to yield a more reliable approximation. Here, we're looking at how a system responds when additional poles are introduced, and we'll walk through an example to understand this better. The goal is to determine whether a second-order approximation holds true for two different transfer functions. Essentially, this means we're checking and simplifying these systems to just two poles. Ignoring the others still gives an accurate enough picture of their behavior. This is important because lower-order models are easier to analyze and design controllers for, but only if they remain valid representations of the actual system dynamics. So, we'll carefully evaluate each transfer function and see if the higher-order effects from the additional poles can be reasonably neglected. Here, we're looking at an example that demonstrates how the system responds when an additional zero is introduced. This is important because adding a zero to a system can significantly change its behavior and stability. By analyzing this response, we can better understand how the system dynamics shift and what implications that has for control design or performance. Keep in mind that even a small change, like adding a zero, can lead to really different outcomes. So it's crucial to study these effects carefully. Here, we're looking at a non-minimum phase system. What makes this system interesting is when it has a zero that is negative, which means the zero is located in the right half plane. This placement has significant implications for system behavior. Unlike minimum phase systems, non-minimum phase systems can introduce phase shifts that are counterintuitive, leading to challenges in control and stability. Understanding this concept is crucial because it affects how the system responds to inputs and how we design controllers to manage that response effectively. Here, we're considering a three-pole system that also includes a zero, as represented in the equation shown. The interesting part to focus on is what happens when a pole and a zero cancel each other out. In this case, when the term S plus P3 cancels with the term S plus Z. When this cancellation occurs, the system effectively reduces to a second-order transfer function. This simplification can make analysis and design much more straightforward because second-order systems are easier to understand and work when compared to higher-order ones. So, The key takeaway is that pole zero cancellation can simplify the system dynamics by eliminating certain poles and zeros that would otherwise complicate the behavior of the system. Let's take a closer look at the concept of steady-state error in control systems, specifically in a unity feedback setup. A unity feedback system means the output is fed back directly without any modification to the input for comparison. Understanding steady-state error is crucial because it tells us how accurately the system can follow a desired input over time. Essentially, it's the difference between the input and the output as time goes to infinity, indicating how well the system performs under steady conditions. Alongside this, we have error constants, which are specific parameters that help quantify the system's ability to minimize this error for different types of inputs like step, ramp, or parabolic signals. These constants provide valuable insights into system stability and performance, allowing us to predict and improve how the system reacts in the long term. Here, we're discussing the different types of systems based on the number of poles at the origin. A type 0 system has no poles at the origin, which typically means it has a finite steady-state error for a step input. Then, a type 1 system has one pole at the origin. This configuration usually results in zero steady-state error for step inputs, but finite error for ramp inputs. Finally, a Type 2 system has two poles at the origin, allowing to track both step and ramp inputs with zero steady-state error. Understanding these system types is crucial because it directly affects how well a system can follow different types of input signals without steady-state errors. Now, let's focus on steady-state error and error constants, which are crucial concepts in control systems. Steady-state error refers to the difference between the desired output and the actual output of the system as time approaches infinity. It's a measure of how accurately the system can achieve its target value after all transient effects have settled. Understanding steady-state error helps us evaluate system performance and determine if the system meets design specifications. Error constants are parameters that help quantify the steady-state error for various input types, such as step, ramp, or parabolic inputs. These constants give us insight into the system's ability to track different types of inputs precisely. By analyzing steady-state error and error constants, we can design controllers to minimize inaccuracies and improve overall reliability. This topic is fundamental for ensuring optimal system behavior in real-world applications. Now, let's dive into steady-state error and error constants. Steady-state error refers to the difference between the desired output and the actual output of the system as time approaches infinity. Essentially, it tells us how accurately our control system can track a desired input or maintain a set output over the long term. Error constants, on the other hand, are parameters that characterize the steady-state error for different types of inputs, like step, ramp, or parabolic signals. These constants help us predict the behavior of the system and design controllers to minimize the error. Understanding how steady-state error and these constants relate is crucial for improving system performance and achieving precise control. On this slide, we'll explore some practical examples related to steady-state error and error constants. Understanding these concepts is essential for analyzing how well a control system performs in the long run. Steady-state error tells us the difference between the desired output and the actual output once the system has settled and stopped changing. Error constants, such as the position, velocity, and acceleration constants, help us quantify the steady-state error for different types of inputs like step, ramp, or parabolic signals. By working through examples, we can see how these constants affect the error and what that means for system accuracy and performance. Let's delve into the specific cases to get a clearer picture of how these concepts are applied in real-world scenarios. When a pole is added closer to the origin, which means it's a low-frequency pole, it tends to slow down the system's response. This results in an increase in both the rise time and settling time, meaning the system takes longer to reach and stabilize at its desired output. Additionally, it can increase the steady-state error because it reduces the DC gain, making the system less accurate in maintaining the target value. Overall, the system becomes sluggish and less responsive. On the other hand, if a pole is added far from the origin at high frequencies, it has little impact on the transient response. However, if this high-frequency pole isn't far enough away, it can reduce noise attenuation, which might introduce unwanted disturbances. If it's much farther than the dominant poles, its effect is practically negligible. In general, adding more poles usually makes the system less stable by shifting the poles toward the right half of the complex plane. This shift can lead to increased overshoot and oscillations, which means the system might become more prone to instability and more difficult to control smoothly. Let's discuss the effect of adding zeros to the closed-loop transfer function. First, when a zero is placed close to the origin, it speeds up the system's response by decreasing the rise time. This means the output reaches its desired level faster. However, this can also lead to increased overshoot because there's less damping in the system. On the plus side, such zeros can improve steady-state tracking for certain types of inputs, helping the system follow the desired signal more accurately. Next, a zero that's far from the origin, often called a high-frequency zero, has minimal impact on the transient response. It mainly affects the system at higher frequencies and can usually be ignored when analyzing low-frequency dynamics, which are often more relevant for control performance. Finally, a right half plane zero or a non-minimum phase zero has a more complicated and generally negative effect on the system. It always reduces the stability margin, making the system more prone to oscillations or instability. Additionally, it causes an undershoot in the time response, where the output initially moves in the opposite direction before settling. While the rise time may actually decrease, the overall settling time is slowed down, so the system takes longer to stabilize. This makes controlling systems with right half plane zeros particularly challenging. Let's take a closer look at how adding poles and zeros affects a system's behavior. Starting with poles near the origin, these tend to make the system less stable. You'll notice the transient response slows down, the rise time, settling time, and overshoot all increase, and the steady-state error also goes up. Conversely, adding poles far from the origin has almost no effect on stability or system response, so their impact can usually be ignored. When it comes to zeros, a zero near the origin can reduce damping, causing the system to respond faster with a quicker rise time, but also more overshoot. Interestingly, this can actually help decrease the steady-state error. Zeros located far from the origin, much like distant poles, typically have negligible effects on system dynamics. Finally, right half plane zeros are particularly important because they reduce the stability margin. They often cause an undershoot in the response and slower settling times. The effect on steady-state error in this case varies depending on the specific system. Understanding these influences is key when designing control systems to achieve the desired balance between stability, speed, and accuracy. Sensitivity measures how much the transfer function changes in response to a change in the system's gain. Specifically, it's defined as a percentage change in the transfer function divided by the percentage change in the gain. In simpler terms, it tells us how the output responds relative to changes in the input gain. By analyzing the transfer function, we can understand the system's sensitivity more clearly. When the feedback gain H increases, the term 1 plus GH also increases, which causes the sensitivity to decrease. Conversely, if H decreases, then 1 plus GH decreases, resulting in increased sensitivity. This inverse relationship means that sensitivity and feedback gain are essentially reciprocal. Higher feedback gain reduces sensitivity, making the system more stable and less affected by changes in gain. Here are the key references that provide a solid foundation for understanding control systems and automation. Norman Needs of Control System Engineering is a classic textbook widely respected for its clear explanations and practical approach. Mohammed Sarwar's article on Medium offers a comprehensive introduction to control systems, making complex concepts accessible. For those interested in the basics of control engineering, Achrome Robotics provides a detailed overview that's very helpful. Lastly, the Joe video link included offers a visual and interactive way to grasp core ideas in control engineering. These resources together cover theoretical knowledge, practical applications, and visual learning to give you a well-rounded perspective on control systems. If you have any questions about these, feel free to ask. Thank you all for your time and attention. I appreciate the opportunity to share this information with you, and I'm happy to answer any questions you may have. Feel free to reach out if you want to discuss anything further or need additional details. Thanks again.